Let us finish our discussion of section 5.1. In this section, we discuss the following boundary value problem: differential equation and two conditions. Question here is the following: find all lambdas such that the whole boundary value problem has a non-trivial solution. Non-trivial means non-zero. Last time we discussed that if lambda is equal to 0, or if lambda is lesser than 0, the boundary value problem has only the trivial solution. Now let us consider case 3. Case 3, suppose lambda is greater than 0. We start with our equation and find the general solution of this equation. We apply the standard procedure. Step 1, find the characteristic polynomial of this equation. Then move lambda to the right, done, and then take square root of both sides. Note that since lambda is greater than 0, the expression is complex. It's exactly what we do over here. Square root of negative lambda is equal to square root of lambda times negative 1. Next step, a root of the product is equal to the product of roots. And we replace square root of negative 1 by I. Observe that this complex number can be rewritten as 0 plus square root of lambda I. We do it in order to apply methods from section 2.2. In section 2.2, we say that if roots are complex and written as alpha plus minus beta I, then particular linearly independent solutions of our equation are this and this. Observe that in our case alpha is 0, beta is square root of lambda. Therefore, particular linearly independent solutions are this. Here we apply formula number 1, and this. Here we apply formula number 2. Lastly, since e to 0 power is 1, particular solution number 1 is cosine, particular solution number 2 is sine. Therefore, the general solution of this differential equation is C1 times cosine plus C2 times sine. It's exactly what is written here. Now it's time to find C1 and C2. Step 1, use condition number 1, y of 0 is equal to 0. The goal is to show that this condition implies C1 is equal to 0. Here's why. Copy of what is written here over here, and then replace x by 0 everywhere. Done. Note that y of 0 is equal to 0. It's exactly what is written here. Also observe that cosine of 0 is 1, sine of 0 is 0. Therefore, the right-hand side is simply C1. So C1 is equal to 0. It's exactly what is written here. Next step, let us find C2. In order to find C2, we use the second condition. Y of L is equal to 0. So once again, for convenience, we copy this general formula over here And then, since C1 is equal to 0, we just discussed, C1 is equal to 0. Let us replace this C1 by 0. Term number 1 disappears, so y of x is C2 times psi. It's exactly what we have here. Next step, replace x by L, done. And lastly, use the fact that y of L is equal to 0. We replace y of L by 0, and we're done. Here's what we do next. Remember, we care about non-trivial, non-zero solutions. Observe that since C1 is equal to 0, C2 cannot be equal to 0, because if both C1 and C2 are equal to 0, y of x is the trivial solution. But we care about non-trivial solutions. Since we care about non-trivial solutions, C2 cannot be 0. Since C2 is not equal to 0, we can divide both sides here by C2. 0 over C2 is 0. C2 times sine divided by C2 is just sine. Lastly, by trigonometry, looking at the graph of sine, we see that sine is equal to 0 only if t is equal to an integer multiple of pi. Therefore, going back to our equation, since sine of square root of lambda L is equal to 0, square root of lambda L is an integer multiple of pi. It's exactly what is written here. Lastly, we divide both sides by L, done, and square both sides. This is a complete description of all lambdas for which our boundary value problem has a non-trivial solution. Moreover, these solutions are: step 1, we copy what is written here, done, and then we replace square root of lambda by n pi over L, done. These are values of lambda for which our boundary value problem has non-trivial solutions. These are the non-trivial solutions. Lastly, we call lambdas for which our boundary value problem has non-trivial solutions eigenvalues, and we call these non-trivial solutions eigenfunctions. In other words, in our particular case, these are eigenvalues because if n is equal to 1, this expression becomes pi square over L square. If n is equal to 2, this expression becomes 4 pi square over L square, and so on. These are our eigenfunctions by this formula. Guys, any questions here?
So in like an actual problem, would L be just some number?
L is some positive number.
Thank you.
Other questions?
For these type of questions, is the square root of lambda always equal to n pi over L?
Please take a look at this. Sine is equal to 0. And looking at the graph, sine is equal to 0 only if the input is an integer multiple of pi. So there is no escape. This is the input. The input is square root of lambda L. Square root of lambda L should be an integer multiple of pi. By the way, you may ask me a question, why here we have positive integer? Looking at the graph, we have either positive multiple of pi or negative multiple of pi. But observe that n pi is equal to square root of lambda L. L is positive, square root of positive, pi is positive. Therefore, in our particular case, n has to be positive.